Recording has started. So yesterday we talked about the difference between capacity and weight, or capacity and volume, I should say. And we saw there was a conversion between them, but it was kind of fuzzy. If I take a tank, let's say that this is 46 inches long, and let's go 28 inches wide, and simply 8 inches tall. I want you guys in your notes to tell me how many gallons that is. We'll go over that.
Okay. I'll be back.
Okay. For our first calculation here, we would be finding the volume of this tank. Volume would be length, 46 inches. This is a simple box. We'll just use the formula length times width times height instead of doing the area of the base times the height. So we get the 46 inches times the 28-inch width times the 8-inch height, which is going to give us a volume 46 times 28 times 8 is 10,304. Of course, inches times inches times inches is inches cubed, or cubic inches. Now, to turn that into gallons, figure 10,304 cubic inches, put them over 1. And we're going to put cubic inches on bottom to cancel them out. Gallons are going to go on top. We have to remember that 1 gallon is approximately 231 cubic inches. The cubic inches cancel out. We've got 10,304 times 1 gallon, which is 10,304 gallons, over 1 times 231, which is 231. We're just going to divide that out. Divided by 231 gives us 44.6 gallons. That would be about,
Sorry about that.
a half gallon tank. The next one we're going to do here let's say that this is, it's 120 centimeters by 60 centimeters by 'I want to know how many liters that tank is. I'll give you about a minute there before we go over it. for this one. Again, we start out by finding the volume. Again, it'll be length times width times height. So 120 centimeters times 30 centimeters. That multiplies out to be 216,000 centimeters cubed. Now, this is volume. Up here we found the volume, but we're looking for capacity. The gallons are unit of capacity. Our conversion to capacity in the standard system, it required us to know that awkward conversion, the 231 cubic inches. Had to do division, calculation. Well, the metric system, as we mentioned yesterday, they planned for this conversion from volume to capacity. 1 milliliter is defined to be 1 cubic centimeter. Because of that, 216,000 cubic centimeters is equal to 216,000 milliliters. Now, we did ask for this in liters, so we do have to do some conversion from milliliters to liters. On the chart, from liters to milliliters, actually from milliliters to liters, it is 3 spots to the left on the chart. So our decimal point has to move that 3 spots to the left. So we go 1, 2, 3, 216 liters. Now, just for fun, let's compare the size of the two tanks. We saw here the conversion within the metric system was way simpler because once we multiplied them up to get a volume, it's just a matter of changing the units to equivalent units and then moving the decimal point to convert. What if we want to compare that to the other tank and I want to put that 216 liters gallons? Well, we would have to look up to know that put liters on bottom, gallons on top. 1 gallon is 3.785 liters. 216 times 1 gallon, so 216 gallons, over 1 times 3.785, so 3.785. 216 divided by 3.785, 57.07 gallons. So this is quite a bit bigger tank than the one up here that was 44.6. When we are converting from metric to standard or standard to metric, there is no way to get around the ugly conversion. Okay, similar to what we did yesterday. Today, we need to talk about the difference between two types of measurement again. Today, however, it's the difference between weight and mass. Start out with the definition. Weight is the force of gravity on an object. Mass is the amount of matter. Matter is material, the amount of atoms, the amount of stuff that's in that object. Big difference between them is how they're measured. Weight is measured using force, while force is measured using a spring. A good spring, if we attach it to something, we just let it lay at rest, has a certain length. So let's say that's the rest length right there. Now if we stretch it a certain distance here, it's going to require a certain amount of force. Now if we double the amount of force, times the force, distance stretched is also 2 times. The distance that spring stretches is exactly proportional, very precisely proportional to the amount of force that's put on. So we can use a spring to measure force very precisely. And so to measure the weight of something, we use a scale. That scale is just a spring that is mounted on some sort of a device that we can have a numbered scale on. That's where the term scale comes from, is the numbered scale. There's an indicator mounted on that, so that when we hang our object on it down here, a hook or whatever, as that pulls down, the indicator moves, and wherever it indicates how far the spring is stretched, which indicates how much force or what the weight is of that object. Mass is measured the balance. The balance is really nothing more than precise, very precision seesaw or teeter-totter. Put our object that we're trying to measure on one side, then we place known masses on the other side until it balances. Whatever this known mass is, that's the mass of our object. All right, so well, why is that such a big deal, such a big difference? Big difference is mass not depend on gravity. What do I mean by that? Well, let's say we go to the moon. On the moon, gravity is about 1/6 of what it is on the Earth. Well, looking at my scale here, that would only pull 1/6 this far. So it would be like this. So the weight would be 1/6 of the weight. Looking at our balance here, the amount that gravity pulls on this object would change, but the amount that it pulls on our known would also change. So the two masses would still balance each other because gravity changes the same for both of them. So the change in gravity does not affect the mass of the object, but it does affect the weight. On Earth, we tend to use the two interchangeably. Gravity is relatively constant on Earth. It's about a 4.5, almost 5% difference from North Pole to equator. So literally, a 200-pound person would weigh about 9 pounds more at the North Pole than they would at the equator. Very small difference. So because gravity is relatively constant on Earth, we tend to use it interchangeably because your weight will be the same no matter where you are, as long as your mass doesn't change. In the standard system, though, we do have a unit for mass. That unit, you probably never heard of it before, is called a slug. A slug, a mass that has a weight of 32 pounds. Fairly heavy. The expression, there's a whole slug of them over there. That's where it comes from, is that unit of a slug.
Why is it called a slug?
Engineering, never see that term used. What was that?
Why is it called a slug?
No idea. That's one origin that I have not seen where that came from.
That is weird.
Outside of science and engineering, I have never heard of it, never seen it used anywhere in practice. Like I said, the standard systems tends to focus on mass, or on weight. Let's start with the larger one. Let's talk about a ton. Typically, we think of a ton as being 2,000 pounds. And it is 99.999% of the time. You hear the term ton in this country, talking about 2,000 pounds. But this is actually what is called one net or short ton. Now the term net implies that there's something called a gross or a long ton. And there is 2,240 pounds. What's the difference? Well, think of your paycheck. If you work 40 hours at $12 an hour, you have earned $480. That is your gross pay. You don't get to keep that. They're going to take taxes and other things out. You get a smaller check. That is your net pay. Similar type of thing here. Ton was originally used for buying and selling grain. Well, you could not put a ton of grain on a scale, it would fall off. So it had to be in a container. The container that held a ton of grain was about 240 pounds. So with the container, a ton was 2,240 pounds. Without the container, net the container, it was 2,000 pounds. Now I put this up here not to confuse you. I'm going to cross it off. We're never going to use that in this class. There might be in the homework, but any quiz or test I give you, I'll be using the regular standard 2,000 pound ton. Smaller than a pound. Now, first of all, let's talk about that abbreviation for a pound, LB. Would have made sense to use PD for pound. But in the bookkeeping system, for buying and selling grain, PD was already used for paid. Wouldn't want to confuse the two. So rather than confuse those abbreviations, they used the Latin word for pound, which was libra. That's where the LB comes from, is libra. Latin libra is a pound. Smaller than pound, we have ounces. And 1 pound in US weight is 16 ounces. Actually, English standard or imperial is 16 ounces. Smaller than an ounce. Now, ounces are abbreviated OZ. Since they used the Latin word libra for the pound abbreviation, they decided to use the Latin word ounza for the ounce abbreviation. Smaller than an ounce, we have drams. Those units that most people have never heard of, there are 16 drams. Drams were one of the original apothecary units. You might be prescribed an eighth of a dram of medication. Smaller than a dram, 1 dram contains 60 minims. Minims could also be used as a unit of volume. They had fluid drams and fluid minims. Things get a little screwed up when we get into the past the units with them. And again, that's not something, we're not going to do drams in this course. Grains. For some reason, grains were always compared to a pound. 1 pound is 7,000 grains. This was grains of sand or grains of salt. Literally take a tweezers and count out 7,000 of them to get 1 pound. And we see grains used a lot in medication. So much to the point where in medical math, they actually had absorbed grains into the metric system for doing dosage calculation. So those are our units of weight in the standard system. Now, before I move on to the metric system, I want to mention one thing. But there are other units out there like stones and hundredweights and stuff like that. Not used enough that it's really important enough for us to do anything with. But you do hear quite a bit. If you listen to any of the financial news, you might hear gold has reached $2,000 an ounce or whatever the price is. Those are not talking about standard ounces. Remember we talked about different rulers at different points in time declaring their thumb is the official inch and their foot and everything else. Well, that happened at different areas. So the inch is different from one region to another. The foot was different from one region to another. The gallon might be different from one region to another. Pounds and ounces were different from one region to another. For years, the center of trade for precious metals in the world was the island of Troy in the Mediterranean Sea off the coast of Greece. So to this day, precious metals are still bought and sold using troy measure. 1 troy pound is a little bit smaller. It's about 0.82 of our regular pounds. Now, with that said, 1 troy pound only contains 12 troy ounces. So you can see the troy pound is smaller than our US pound. But the troy ounce is a little bit larger than our US ounce. So when they say gold has hit $1,900 an ounce, they're not talking about our regular ounce that we normally use. Something slightly larger. Now it's not significantly larger, but just enough to make a difference. It's still, a regular ounce would still be pretty pricey. The reason I bring this up is I've actually seen it a couple of times in the last few weeks. People on Facebook Marketplace and other buying and selling places offering to sell silver or gold bars. I'm saying this is how many ounces it weighs and this is the price per ounce. Yes, it may weigh that many ounces and that may be the price per ounce, but that price per ounce is not talking about regular ounces. So don't get yourself cheated on something like that. Make sure you're talking about the correct units. Let's talk about metric. In the metric system, they tend to focus on mass rather than weight. So we are going to talk first about metric weight. Unit of weight, actually the unit of force in the metric system even. Now because the Newton depends on gravity, it doesn't fit into the nice, neat little mold of the rest of the units, everything being multiples of 10 or whatever. 1 Newton, actually I should put that the other way around, 1 kilogram would actually weigh about 1 Newton under the standard force of gravity. Right, that 1 kilogram would be 9.8 newtons. So Newton is actually a fairly small unit of force. Much smaller than a pound, to be honest. But like I said, metric tends to focus on mass. And in the metric system, the unit that is defined for mass is the gram. Now, we had mentioned yesterday that they planned this system out so that the conversions were pretty nice. 1 milliliter, we said, was 1 cubic centimeter. They set those equal so that we could convert rather easily. Well, they did something very similar with the gram. The gram is defined to be the mass of 1 milliliter of water. Now, they did define it to be 1 milliliter of distilled water, just so, because there is a slight difference in mass depending on what's dissolved in the water. So it's pure water or distilled water. That's a pretty nice connection that we can make that without. Otherwise, we look at our standard conversions. What is a gallon is 8 pounds of water. That's not a very neat conversion. So our gram, it's just like any other metric unit. Decigram, centigram, gram. They skip the 10,000 and 100,000. They go to microgram. They would keep going down to nanogram, but we don't go quite that low. Going larger, they have decagram, hectogram, and kilogram. And again, we skip 10,000, 100,000, goes up to megagram. Now, some things to mention here. Again, the gram, the kilogram, and the milligram are the ones that caught on. The other ones never really caught on. They exist, but we don't really use them for anything. Micrograms get used a lot in medicine. But in medicine, again, as we mentioned, because of that need to keyboard everything into a computer, instead of using that Greek letter mu, they use MC. So they might use MCG for microgram. You see that, that's what it stands for. The other thing I want to note is the megagram. For megaliter, that was just way too large. It was 284,000 gallons. That's huge. a megameter, well, a megameter would actually 15 megameters around the whole 25, sorry, megameters around the equator of the Earth. It's just too big of a unit to be practical. The megagram, however, is practical. Megagram, of course, is 1,000,000 grams. Or if I convert that from grams back to kilograms, that's only 1,000 kilograms. That's a very important unit, mainly because 1 kilogram equals about 2.2 pounds. It's technically 2.208 or something like that pounds. We'll just go about 2.2. What is that? Why is that so significant? Well, if I take my 1,000 kilograms, put it over 1 kilogram, 2.2 pounds. Kilograms cancel out. 1,000 times 2.2 pounds is 2,200 pounds. It's a little bit larger, but that is very, very close to our standard pound, or 2,000 pounds, or standard ton, I should say, 2,000 pound ton. Because of that, the 1,000 kilograms, or the megagram, is often referred to as 1 metric ton. This is another thing to be careful of if you listen to the farm report or any of the commodities reports. I know they're very interesting listening. You'll hear them talk about, wheat traded for a certain dollar amount per metric ton and whatever. That's what they're talking about, is metric ton. A little bit bigger than our standard ton. So if I asked you, find the mass in kilograms if this tank is filled with water. So let's say that this is 40 centimeters, 25 centimeters, and 15 centimeters. This adds a step to that calculation we did at the beginning of class. We're going to start out finding the volume. Length times width times height. 15,000, I believe, centimeters cubed. For capacity, 15,000 centimeters cubed is just 15,000 milliliters. Mass, 15,000 milliliters. Again, this is filled with water. 1,000 milliliters of water is 15,000 grams, which we do have to convert grams to kilograms. That would be 15 kilograms. That's not that terrible, not a bad conversion. Go back to our standard units, however. Let's say that we have 15 inches here, 10 inches, and 7 inches. Well, we start out with our volume. Our volume would be 15 inches times 10 inches times 7 inches. 1,050 cubic inches. Change this to capacity. 1,050 cubic inches, we'll put it over 1, times, cubic inches go on bottom, gallons on top. 1 gallon is 231 cubic inches. Cubic inches cancel out. 1,050 gallons over 231. Giving us 4.55 gallons. And then we can go into weight. .55 gallons at 1 gallon equals 8 pounds. Gallons cancel out. We take the 4.55 times 8, 36.36. So you can see how that is not near as easy as the metric calculation up here. Metric, once we calculate the volume, everything else was just moving decimal points for the units. There's no calculation left. You get from volume to capacity to mass. Here, to get from volume to capacity, we had to do an ugly conversion, and then another one to get from capacity to weight. If I want to compare the size of those two tanks, by the way, let's do it. Got 36.36 pounds. That over 1. Pounds on bottom, kilograms on top. We look up our conversion. 1 pound or 1 kilogram is 2.2 pounds. This is 36.36 divided by 2.2. 16.53 kilograms. This up here was only 15 kilograms. So this tank is slightly larger. Hopefully you guys are getting the hang of using this dimensional analysis, that conversion factor to convert units. It is an extremely powerful tool. It can be used for a lot of calculations. Even if you're not sure what the formula is, the units can tell you what calculation has to be. Like I said, when you get into medical math, if you ever do EMT work or anything like that, your dosage calculations are 90% dimensional analysis. Okay, so for right now, out of that packet, there's page 238 dealing with standard weight, problems 51 through 56. And page 266 dealing with metric mass, problems 49 through 54. We have about 15 minutes left here if you'd like to get started. I'll be here to answer any questions. Otherwise, that is it for the day.